Hello, Math 137 friends. Welcome to 8.3, an introduction to parabolas. A parabola is a shape that's formed when we graph the quadratic equations. Now, when we graph linear equations, like y equals mx plus b for certain values of m and b, we know we always get straight lines. Anytime we graph a quadratic function, so just remember what a quadratic function is. In standard form, ax squared plus bx plus c, where a is not equal to 0, because if a was 0, we would have a linear equation. Power in the variable would be 1. Highest power in the variable would be 1. Here we have a quadratic equation, so the highest power in the variable is 2. And anytime we graph a quadratic function, the graph always takes on the same basic shape. So here's an example of a parabola. This is a right side up or a positive parabola. It may be upside down. We won't talk about left to right parabolas in this class. We do talk about that in pre-calculus because those would no longer be functions. They still can be graphed, but they're just not functions. We're only talking about quadratic functions. So right side up or positive parabola, upside down, negative parabola. Our parabolas may be wider and more spread out, or they may be tall and narrow, like this. So what we're going to do is look at equations and how can we determine from the equation the shape that our parabola takes. So our first example is just the most basic quadratic function, y equals x squared, or f of x equals x squared using function notation. Leading coefficient is a, b and c are both 0. So just a side note here, notice that I put a cannot be 0 because we would eliminate this leading term and would no longer have a quadratic. So here a is 1. So I'm just going to plot a few points to get an idea of how this behaves, because when in doubt, when you're asked to graph a function and you're not sure what the general shape is yet, you can always choose inputs, find the corresponding outputs, and plot those points. So I know the domain of this function is all real numbers because I can square any value, so I'm allowed to put in anything for x. So I'm going to start pretty simple. I'm going to start right at x equals 0. If x is 0, 0 squared produces an output of 0. And then I'm going to move to the right on the number line. At 1, 1 squared is 1. 2, 2 squared is 4. 3, 3 squared is 9. 4, 4 squared is 16. And I can see that 16 is going to be way up here. We're going to be at this point right here. I know at 5 I'm going to be at 25, which is off my grid. So I'm going to stop there. I'm getting the feeling on how this function behaves. The larger the input, the larger the output. So I'm going to move to the left on the x-axis. If x is -1. Now be careful, keep in mind when you square a negative number, the result is always positive. -1 times -1 is +1. -2 times -2 is +4. -3 times -3 is 9. And I can see that I have this mirror thing going on here. So let's plot these points. The point 0, 0. At 1, I'm at 1. At 2, I'm at 4. At 3, I'm going to go up here to 9. At 4, I'm going to be way up here at 16. All right, so we can see this pattern here that's not a straight line. It starts out less steep down here and it gets steeper as we move to the right. And I know at 5, I'm going to be way here up here at 25, so I can fairly conclude that this graph is going to go up forever as we move to the right. Now let's plot our values to the left of 0 on the x-axis. At -1, we're at 1. At -2, we're going to be at 4. At -3, we're going to be at 9. And at -4, we're going to be at 16. So I see the same behavior as we move to the left. It's going to head in the northwest direction. And what I observe here is it goes up as I move to the right, it goes up to the left. We see this mirror image. If I put a line right here, if I look at this line, the y-axis, I know I can fold the graph on this line and it's going to be a mirror image on each side of itself. That is, it exhibits symmetry with respect to the y-axis. So here, let's just put a few key facts. The domain of this quadratic function is all real numbers. We're allowed to put anything in. So to represent all real numbers, we use the interval from -infinity to infinity. And if we go back and review our chapter to stuff, the range is all output. So if we look at either in our table of values and look at how the outputs behave, or we look at our graph, notice that all the outputs are above the x-axis. So the smallest value of y is 0, and then from that point on, they all move up. So y goes from 0, and then there's no upper bound. So the domain, we're allowed to put anything in. When we put all values in that we possibly could, hypothetically, because obviously we can't stick in every value, we are going to get the set of non-negative numbers. So this is the general short form. This is the most basic quadratic function. We can move it to the right, the left, up, down. We can flip it over. And depending on the values of the coefficients in front of x squared, x, and the constant at the end, will determine how this parabola behaves. All right, so before we get into those details, let's make a list of things that are important features of all parabolas. Right, all parabolas have either a low point or a high point, the top of the bottom of the valley, or if it's an upside down parabola, it would be the top of the hill. And based on the equation, we can find the coordinates of this point. And this is called the vertex. Whoops, vertex, if I can spell correctly, that's the vertex of the parabola. There's a vertical line that goes through the vertex. It's just an imaginary line, that's why I drew it dashed. But this is a line that we can fold this on, and this quadratic function would be a mirror image of itself with respect to that line. In this line, we call the axis of symmetry. All quadratic functions graphically have an axis of symmetry. Right here, this point right here. So here's my y-axis, here's my x-axis. This point right here, where the quadratic function crosses the y-axis, is called the y-intercept. As a matter of fact, where any graph crosses the y-axis is called the y-intercept. So all quadratic functions have a vertex, an axis of symmetry, and a y-intercept. In this particular example, we see that this quadratic function crosses the x-axis 2 times. Now we're going to see not all quadratic functions have x-intercepts. Oops, sorry. Would be my kitty. Sorry. Oh no, Mookie. Whoops, she just fell off the table. Sorry. Morning entertainment, x-intercepts. Okay. Our quadratic functions may or may not have x-intercepts, depending on where it falls. If the vertex falls above the x-axis and it opens up, then it would not have x-intercepts, or if the vertex falls below the x-axis and it opens down, it also will not have x-intercepts. In higher level maths, we talk about the end behavior. So we will throw that out there for those of you that plan on continuing on. That is end behavior. Sorry, my pen got a little bit, it's smudged together. It's how the arrows, the direction in which the arrows point. So those are the important things we're going to look at. We're going to determine the domain and the range also of all our quadratic functions. All right, so that being said, let's make a list. All parabolas have exactly one vertex, all parabolas have exactly one y-intercept where it crosses the y-axis. All quadratic functions have an axis of symmetry, just one. It's the vertical line that passes through the vertex. And parabolas can either have 2, 1, or no x-intercepts. It has 2 x-intercepts if it crosses the x-axis twice, like in this scenario, 2 x-intercepts. It has 1 x-intercept if its vertex falls on the x-axis, like in our original graph of y equals x squared, the vertex fell at the origin. I know it's really not an intercept in the strict sense of the word. It doesn't cross the x-axis, but it does touch the x-axis, so we count that as an intercept. Or if the vertex falls above the x-axis and the parabola opens up, we will have no x-intercept. So 2 x-intercepts. This is the 1 x-intercept case, and this is the no x-intercept. We could flip these over, see how this scenario would play out if we had upside down parabolas. We had an upside down parabola and the vertex fell above the x-axis. That would be our 2 x-intercept case. If it was an upside down parabola and the vertex just sat on the x-axis, that's also the 1 intercept case. And then no x-intercepts, when we would have a vertex below the x-axis and it opens down. Right, so for the sake of this class, all our parabolas are either going to open up or down. There are situations where parabolas open left or right, but they're not functions because remember, in order to be a function, you have to pass the vertical line test. And if our parabola opened left or right, it would fail the vertical line test. So we don't consider those here. A parabola opens up, it looks like this. And we call this a positive parabola. It opens down. When the arrows point down, it looks like an upside down bowl, and this is called a negative parabola. So remember, this is parabolic functions. We can have parabolas that open left and right, but those are no longer functions. They're just called conic sections, and we talk about those in pre-calculus if you decide to take it to that level. All right, so given a quadratic equation in standard form, how can we determine or identify all these features? All right, so standard form of a quadratic function, ax squared plus bx plus c. The graph behaves as follows. It opens up when your leading coefficient is positive. So the leading coefficient is going to determine if this quadratic function opens up or down, and opens down when your leading coefficient is negative. Now remember, the leading coefficient will never be 0. To find the vertex of the parabola, that bottom point, very bottom point of the bowl, or the top point. Well, given the quadratic function in standard form, remember to find the zeros or to solve this quadratic equation, we would use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So here's a reminder. This gives us lots of information. Remember, the discriminant told us how many zeros would have and what type. Well, this other part right here, without the plus or minus, determines where the vertex is. So the x-coordinate of the vertex is always the opposite of the coordinate in front of the x term, all over 2 times the leading coefficient. So this part of the quadratic formula gives us the x-coordinate of the vertex. And to find the y-coordinate, because the vertex is an ordered pair, you're going to plug this number back into the function to find the y value associated with it. So you plug in the value you got for x. So your x-coordinate back into the function to find y. Don't worry, we'll go through examples, all of this. And a vertex has coordinates, so you need to find both the x-coordinate and the y-coordinate. The vertex is an ordered pair. Now to find the equation of the axis of symmetry, well, if you remember, all vertical lines have equation x equals some number. So it is an equation, and this is one of the questions that students get wrong most often in ALEKS just because they forget the notation. It has an equation, x equals, and it's always the x value of the coordinate of the vertex. So negative b over 2a. So be careful, there's 3 parts. You need all 3 of these. So you need all 3 parts. The x, the equal, and the negative b over 2a value. So again, the biggest mistake students put into ALEKS, they'll say, what is the equation of the axis of symmetry? And they'll just write the numerical value, whatever negative b over 2a came out to be, and they'll forget the x equals. All vertical lines have equations, x equals some number, so you have to put in x and the equals. Again, you'll see that when we do examples. Okay, all quadratic functions have a y-intercept. To find the y-intercept for any function, you just set x equal to 0. So if you set x equals to 0, you get the corresponding value on the y-axis. So set x equals to 0 and solve for y. In the quadratic function in this form, the y-intercept is always 0 is my x coordinate. If we plug in 0 for x, this term and this term disappear because x squared and x both are 0, and all that's left is c. So in standard form, the y-intercept is always the number dangling on the end. Only if it's in this form, though. We'll talk about another form in our next lecture. The domain of all quadratic functions is all real numbers. Negative infinity to infinity. All real numbers. All quadratic functions have domain all real numbers unless otherwise stated. It's an application problem and the author of the problem needs to restrict the domain. They will let you know. And the range depends on the y coordinate of the vertex. So once we find the vertex of the equation, we determine if it opens up and down. We find the x and y coordinate of the vertex. Once we have the x coordinate, we know the axis of symmetry. And when we have the y coordinate, we know the range of the function. So what do I mean by that? Well, let's suppose we have a quadratic function that opens up like this, and the coordinates of the vertex are x, y. Then the range would be, well, all my y values on the quadratic function fall above this y value. So the smallest y value would be y, whatever that value is, and then they would, all the other y values would go up to infinity. If it was an upside down quadratic function, and the coordinates of the vertex were x, y, every y value here falls below this one. So the range would be, well, everything below y is represented with negative infinity to y. Now this notation is important. It includes the y value, but does not include infinity or negative infinity. All quadratic functions also have a maximum or a minimum value. If it's a right side up parabola, it will have a minimum value. That's the lowest it goes. If it's an upside down parabola, it will have a maximum value. That's the highest that it goes. So if it is a right side up parabola, the minimum value would be right down here. It's an upside down parabola. The maximum value would be right here. And we'll see this in examples. And then lastly, your quadratic function may or may not have x-intercepts, depending on the value of the discriminant. So if we have the quadratic function in standard form, ax squared plus bx plus c, it all depends on the discriminant. If b squared minus 4ac, that's that value under the radical in the quadratic formula, is negative, we have no real zeros, thus no x-intercepts. So if your discriminant is negative, you're going to have a quadratic function that falls either completely above the x-axis or completely below the x-axis. If your discriminant equals 0, you have one real 0, you have one x-intercept, and it's the vertex. So this is the scenario where quadratic function sits right on the x-axis or just touches it from below. And lastly, if b squared minus 4ac is positive, we have two real zeros, and thus we have two x-intercepts. Oh, I'm running out of room, but I'll squeeze it in. A right side up parabola with a vertex that falls below the x-axis will give us two x-intercepts. An upside down parabola where the vertex falls above the x-axis will also give us two x-intercepts. All right, so I'm really high on time here, so I'm going to say to be continued in part 2 with our examples. So follow up with our next video, 8.3 part 2.